All right, well, good morning, everybody, or afternoon, whatever time zone you're in joining right now. It's my pleasure to chair this webinar for ISEA, the International Statistical Engineering Association. Before I introduce Stefan and give a brief overview of him and what he's about to talk about, I want to advertise a few things coming up with the association. We've got a number of exciting events happening over the next couple of months. In July, we have another webinar that you might be interested in. We're going to have a group of presenters talk about the ISEA's handbook, which is a book meant to explain what statistical engineering is and talk about some of the ways of thinking about problem solving that are sort of innate to statistical engineering, talk about some of the tools and some of the ways we think about doing statistical engineering in practice. So if that's of interest to you, watch out for information in our newsletters and on the website. That's going to be happening sometime toward the end of July. And then in November, we have our annual summit. Last year, the summit, because of the pandemic, it was broken into multiple webinars over a series of months, but this year we're going to do a proper virtual conference. That's going to be happening in November, just before the US Thanksgiving long weekend. And more details will be released closer to that date, but put that on your sort of calendar. We're really looking forward to that. Okay, so with that out of the way, let me introduce Stefan Steiner. Stefan is a professor and department chair in the Department of Statistics and Actuarial Science at the University of Waterloo. He's also the chair of ISEA, and his research interests broadly span the areas of business and industrial statistics. Generally speaking, he likes to think about the development of innovative ways to use process data, excuse me, and statistical methods to drive process improvement and variation reduction. And that sort of research interests are really grounded in practical problem solving that I'm excited to hear about today. Today he's talking about statistical engineering, an algorithm for variation reduction. So Stefan, I'll turn it over to you. And then I'll remind all of the participants, if you want to ask questions, please do so in the question feature of GoToWebinar. If it seems appropriate, I might interrupt Stefan partway through and have your question asked in near real time. Otherwise, we'll save the questions for the end. Okay, so go ahead, Stefan.
Well, thank you, Nathaniel, for that introduction. And I would echo that. I'm going to hopefully leave some time for questions at the end, but if you have questions, say, of clarification nature, then please mention it immediately and we can try and resolve, and probably other people have the same question. Anyhow, so yes, good morning, or maybe good afternoon, or whatever. Really happy to be here, and I'm glad that you're here as well. So I'm going to be talking about statistical engineering as applied to variation reduction, and try and put statistical engineering into a bit of a context in terms of the application area of variation reduction. So here's sort of what I'm planning to cover today or this morning. Have a little bit about me, a little bit more introduction to me, and then I'll talk in general terms about statistical engineering as defined by perhaps ISEA, and then turn to the relationship between that and the context of variation reduction. And as Nathaniel mentioned, I'm going to talk a little bit more about what I've called the statistical engineering algorithm, and I've referred to it as StatEng, just to distinguish it from statistical engineering, the broader concept. And then I wasn't sure exactly what would be best to talk about. Honestly, there's a lot of material I would love to cover, but I thought I'd have to pick and choose a little bit. And I thought it might be interesting to talk in more detail about what I refer to as the 7 variation and reduction approaches that are listed here. And of course, we'll come back to those, and I'm going to explore them in a little bit more detail, provide some examples, and hopefully convince you that these are the 7 ways you can reduce variation in a process. So maybe that'll be controversial, we'll see. All right, so a little bit of background of me. So I'm at the University of Waterloo, and we have at Waterloo a faculty of mathematics. You may not be familiar with it, but it is, I would argue, one of the largest concentrations of mathematics, statistics, and computer science talent in the world. We have a very large faculty, over 8,000 students, as I mentioned, large number of professors, 5 different units, lots of different courses, and so on. So it's a very exciting place, really great place to work. I also involved with the Business and Industrial Statistics Research Group, which as it turns out, Nathaniel is now the director of, but it's been around at Waterloo since 1985 under different guises. It used to be called the Institute for Improvement in Quality and Productivity. And our goals are just to basically promote quality and productivity improvement. And we do consulting and training courses and so on. And at that website listed there, you can get some more information if you're interested. As Nathaniel mentioned in his introduction, I'm going to talk a little bit about the statistical engineering algorithm, and I want to emphasize that it's based on practical experience from both myself and my co-author, Jacques MacKay. And just to give you an idea, this is sort of a partial list of some of the consulting activities that I've been involved with in various companies around the world. So I don't want to belabor that, and I want to get to the material. So as I mentioned, the talk is going to be about statistical engineering and applying it in the context of variation reduction. So I want to explain a little bit more of what I mean by that and how it works, I guess. So statistical engineering, you're all here at this webinar, and presumably you know already about ISEA, the International Statistical Engineering Association, and what we're trying to do. And just to make sure everyone's on the same page, here's sort of the definition of statistical engineering as given by Hoerl and Snee and others, and also promoted on the ISEA website. So you notice that it's, well, you can read it, study of systematic integration of statistical concepts and methods and tools, often with other relevant disciplines to solve important problems sustainably. So as you see that definition, you can see that it's quite a broad mandate, right? We're going to try and solve sort of problems, hopefully important problems, and we're going to use a variety of tools and methods and so on. So maybe to make it a little bit more concrete, there's all this sort of framework or roadmap to help people trying to solve problems understand sort of the various steps that you might need to go through to help you get to a solution that's sustainable. And you can notice again that the focus here is on sort of the tactics. So we're not an association that's really trying to promote particular statistical tools or methods, but we're all about sort of the integration of these methods and using them to solve important problems. So the focus is on sort of the tactics. How do you take tools, maybe often many existing tools, and use them to solve problems? So that's sort of the bigger picture of what statistical engineering refers to nowadays. How does this relate then to the variation reduction context? So most of my consulting work, if you looked at the list, would be sort of in the industrial statistics, variation reduction, process improvement area. And I guess Deming summarizes it very well that he thinks that basically really important for managers to know about what reducing variation can do for you. What can it do for you? Well, so here are some of the ideas, right? If you have too much variability in your products and you can reduce that variation, you can improve their function. Obviously, customers may be happier. In fact, you can even reduce overall costs, less scrap, rework, and so on. So reducing variation is a very important concept, and certainly in manufacturing, but other areas as well. So that was a very strange transition there. Sorry. So process improvement. What am I getting at here? So I'm going to talk about variation reduction and process improvement sort of interchangeably. So when I'm talking about improving a process, you're going to improve some, say, critical to quality output characteristic of the process by reducing the variation in that output. And that way you're going to improve your process. So I'll give you a more concrete example. This is obviously a pretend example here, but suppose your critical to quality characteristic is this deviation, say from some nominal, 0 is the target, and the dashed lines, the dashed vertical lines in this plot or histogram represent, so the specification limits that have been proposed by the process engineers. And if the histogram here represents sort of a representative sample of products from your process, you can see that we have indeed, in this case, a problem with too much variability. There are parts with deviations here near -3 and +3, and those are outside the specification limits of -2 to 2. And so this is a not a very capable process, and we would like to reduce the variability. In other words, we'd like to make this histogram narrower, more peaked, and so thereby get more parts within specification and also more parts, maybe more importantly, more parts near the target value of 0, and thereby improve the process. So this is obviously a laudable goal. I think for this audience, I probably don't have to convince you that reducing variation in this process would likely make the process better, make our customers happier, and so on. The question is, how do we go about trying to do this? How do we understand the process enough to figure out how to reduce the variability in the process? And as I mentioned in my introduction, we're going to get to this idea of what I refer to as the 7 variation reduction approaches, and they'll be presumably relevant for this kind of problem. So obviously this is a problem that's existed for a long time, and people have thought about how I might go about solving this problem quite a bit. And so a lot of the techniques or systematic approaches for variation reduction build off of things that are in the literature. For instance, this diagnostic and remedial journey as discussed by Joseph Juran. And so the diagnostic journey, despite the fact that it doesn't immediately solve the problem, is probably still useful. The idea there is we would think about our process, maybe collect some data, understand why, why is there so much variation in the process? So in other words, we're going to search for the cause. And in my terminology, I wanted to try and identify the important, what I call varying inputs. So any process might have many important outputs. We're looking at only one here, but it also has many process inputs, including things like the operators of the machines, the characteristics of the raw materials, the settings, the speed of the various machines that are running, and so on. And so all these things, a lot of these things are what I refer to as varying inputs. So there are things, inputs to the process that vary as the process is running. And so if we're looking for a cause of variability, why was that histogram on the previous page so wide? Well, it's got to be due to something, and it's got to be due to things that are actually changing in the process. So these so-called varying inputs. So the first step in solving a problem like this is typically, although not necessarily, to try and search for the cause, to try and do this diagnostic journey. Now, as I mentioned before, though, this actually doesn't solve the problem. Just knowing what the cause is doesn't make your process better. But then the next step, of course, is the so-called remedial journey, where we're going to search for a solution. We're going to, if we've successfully completed the diagnostic journey, we're going to use the knowledge we've gained and to try and figure out some way of making the process better, either by eliminating or reducing the effect of that identified cause of variability. So in other words, we're going to change the process somehow, right? We can't expect this process to have less variability unless we change something in the process. And so here the focus moves from what I call the varying inputs to fixed inputs. So things that are normally fixed in the process. So these may be things like the control plan that we have for the process, or the engineering diagrams for how this part is supposed to look. We could change the nature of those things to try and understand or try and reduce the variability in the output. But we have to change something that normally does not change to make this process better, because otherwise it's going to continue the same way it is going, and maybe probably more likely to get worse as things go on. In any case, so this is sort of a framework that we can use to try and understand how we might solve variation reduction problems. So I'm sure all of you have heard of Six Sigma and DMAIC. So this is another sort of framework, if you like, for helping people understand how they might organize themselves for solving some of these problems. Notice that it's got within it this idea of the diagnostic journey and the remedial journey. We're looking for cause and effect relationships, and we're trying to improve, and so on. So it's building and adding a few additional steps that are quite useful to help people and teams figure out how to solve process improvement or variation reduction problems. So as I maybe alluded to already, so statistical engineering, the broad concept that I described earlier, is a sort of a very general purpose problem solving scheme. Six Sigma and DMAIC, I think, in my thinking at least, is a sort of a general purpose process improvement system. So it's designed for helping people understand how to tackle a process improvement problem. So I want to contrast that maybe a little bit with what we refer to as the StatEng algorithm, a statistical engineering algorithm. And this comes from this book that I wrote together with Jacques MacKay in 2005. And maybe before I get into it, I should mention that, as I hope all of you are ISEA members. If you're an ISEA member, then on the members only section of our website, you can get an electronic version of this textbook if you're interested. So have a look for that. So how is this different from statistical engineering, the broader concept, and say Six Sigma, DMAIC, and so on? Well, one difference is that it's more targeted. So it's a particular algorithm designed, as it mentions here, for reducing variation in an existing process. And I have added the words medium to high volume because I'm sort of assuming that you can collect data from this existing process. It's not like you're only making very few products and you can't get much data about what's going on in the existing process. So that obviously is a narrower concept, narrower scope than the other frameworks that I've just introduced in the last few slides. But there are, I think, some advantages to being more focused, more specific. And one of the things and I'll maybe elaborate on this later in the talk, one of the things that you gain is that you can be more prescriptive about how to help people trying to solve these problems. You can use knowledge that have been gained in solving a lot of problems like this and try and distill those nuggets of experience into something like an algorithm like this that describes the various steps that you need to go through to try and reduce variation in an existing process. So it seems perhaps on the face of it fairly similar to things like DMAIC, but of course there are, as you're looking at it, I hope you'll see that there are some particular differences. And as I mentioned earlier, we're going to talk in a little bit more detail about that big middle box there, where we're going to choose a variation reduction approach. And there's the list of the 7 variation reduction approaches again. So you notice that something like that does not exist in DMAIC, and clearly does not exist in something like the broader concept of statistical engineering. No, it's not really a criticism, because those frameworks are designed to be much more general in nature. So it's harder, I think, to come up with a list of very specific things for people to consider. But clearly, if you had a problem that fell into the framework that I'm describing here, and you're trying to reduce variation in existing medium to high volume process, then getting more guidance from people with experience solving problems in that context would probably be helpful. Now here, at this point in the talk, I could have gone in a large number of different directions, I think, to try and give you more information about how this algorithm would work and what are the sort of distinguishing features of this algorithm, say, comparing with DMAIC. And I obviously don't have time to cover everything in the short amount of time we have. And obviously, you probably don't want to hear all of it now anyway. So I made the executive decision, I guess, to talk specifically about the variation reduction approaches. But before I do that, I think I do need to provide a little bit of background to make it easier for you to understand, in a sense, the differences and of the variation reduction approaches that I'm going to describe later. In particular, the box sort of right underneath, maybe I can use my mouse here. This box here talks about finding and verifying the dominant cause. So again, there's the flavor of Duran in here, in the sense of the diagnostic journey and the remedial journey. So this box in the algorithm here, this box is the one that's primarily the one devoted to the diagnostic journey, where we're looking for the cause of variation. And you notice I put a lot more emphasis in the algorithm here on things like looking for a solution, the remedial journey, which I think is missing from some other frameworks, or at least not missing, completely missing, but doesn't give enough, you don't giving enough information, I think, in other frameworks like the Shannon system and even DMAIC to some extent. So in this algorithm, the focus on the remedial journey is both here in the big box, but also the last 2 steps of the algorithm, where we're trying to understand how we might solve the problem. So as I said, I'm going to go into a bit more detail about all these things, but I wanted to also provide a little bit more information about this notion of the dominant cause, because it's important to understand, I think, the distinction between some of the variation reduction approaches. So the next thing I'll do is go into a little bit more detail on the dominant cause. Oh, actually, forgot about this. I wanted to reiterate this idea of what Jeroen de Maas called the power versus generality trade-off. And so you have this idea where, Six Sigma, DMAIC, the statistical engineering, the broader concept as defined by ISEA, are these very general process improvement or problem solving systems. So you sense you're looking at using this maybe a Swiss Army knife. Lots of different options, lots of different choices to make about how you might want to use the various tools. Whereas the StatEng algorithm is very focused on a particular context. So maybe that's just reiterating things I've already said, but I guess I wanted to make sure I didn't miss that point, because I think it's an important comparison between the StatEng algorithm and these other frameworks. So maybe now going on to the dominant cause, and this also may be somewhat controversial. I'm going to claim that in most processes there's a dominant cause, and I'll try and describe what I mean by dominant cause. So when you're in this journey of the diagnostic journey, when you're looking for causes, as I mentioned, we're going to be focusing on things that normally vary, inputs to the process that normally varying. The idea behind a dominant cause, which is I should acknowledge is borrowed from the Shanian system. If you're familiar, you know the concept of a red X. So this is the same sort of idea, that we're going to assume, or we think, that it's likely that there's one or a few of the inputs, varying inputs, causes, if you will, that are dominant in their effect. And so this comes from also Duran. If you look at his book, he talked about the vital few and the trivial many when referring to causes. So the concept is, again, that there are a few causes, maybe a very small number of causes that have an overwhelming effect on the output. And then there's many, many other varying inputs or causes that have very little impact, that are probably easily ignored. And that's, again, a similar concept from the Shanian system, where they talk about the red X and the pink X and so on, where the red X is the cause that has the primary, is a primary driver of variability in the output of interest. And this is in fact not a new concept at all. It's sort of an application of the Pareto principle, the 80-20 rule, to causes of variation. Now, the Pareto principle, if you're familiar, it's been used to examine phenomena in many, many different fields. I think originally it was promoted as a way of looking at land ownership in Italy, where 20% of the people controlled 80% of the land resources. And so this kind of a concept, the idea that there are a small number of individuals or causes that have an overwhelming effect, is very common in many, many different disciplines and application areas. And so it's not too surprising, at least I think, that it could also be applicable in the area of looking at various causes and trying to figure out which ones have the biggest impact. I should maybe also acknowledge that I talk about it as a dominant cause. It sounds like there's only one, but reality is that there could be a small number of individual causes that have a big impact, or maybe even it could be more complicated. It could be an interaction between 2 or 3 or whatever causes. But typically, you're not having to worry about all the different varying inputs in your process. What you want to do is try and find out which one or ones have this large effect. And so that's the goal, I guess, in the diagnostic journey. Perhaps to further understand the dominant cause, here's some sort of pictures to give you a description of what I mean by what is a dominant cause. So I'm going to talk about this idea of a full extent of variation, and that's going to refer to sort of the range of values I have seen for the output in my process. And these diagrams perhaps don't do it really justice, but if you look sort of at the range of values on the vertical axis in these plots, suppose that's sort of the range of values that I've seen in my process. And if I want to know what the cause is, I need to explain why there are output values near the bottom of that range and at the top of the range. And that's what I call the full extent of variation. And so here you can see that if I could find, in the continuous case, that cause that's listed there, it seems to have a very strong predictive power on the output. So if I could find whatever cause is on the horizontal axis on the left plot, that would be the dominant cause. Like if I could find out that cause, I would have a strong leg up, I guess, in terms of solving that problem. And you can imagine various things I could do. Maybe you're looking ahead to the variation reduction approaches. One obvious thing I could do is just reduce variation in that cause. If I could reduce variation in the horizontal axis, it would naturally result in less variation in the output. Now, of course, that may be expensive and so on, but that's one option. Similarly, the cause might be a discrete. There might be 4 different values, categorical cause. and the value of the average output value just changes quite a bit when I change the value of the dominant cause. And so again, we have a clear dominant cause, and you can sort of get an idea of why this is dominant. If I could align these sort of groups of red dots corresponding to the different levels of the dominant cause so that they all sort of had roughly the same average, then the overall variability, the full extent of variation in the output would be dramatically reduced. So that's clearly what I refer to as a dominant cause when there's a discrete, when the causes are discrete. And so the idea as I mentioned, is the diagnostic journey is to look for a cause that has this sort of effect. So perhaps to make it a little bit more concrete, I wanted to make this talk pretty math-free, but there's one equation here, bear with me. So I wanted to try and motivate or convince you, perhaps. You may not be convinced by the idea that there is a dominant cause, but perhaps I could convince you that if there's not a dominant cause, it's going to be hard to solve the problem. So maybe we should just hope that there is a dominant cause. And so to quantify that a little bit, here's supposedly an equation. So we got an equation that relates the output y with, say, some function of x, which may be linear, or some simple function, could be something more complicated, plus some unexplained variation corresponding, I guess, to all the other varying inputs and measurement error and everything else. So I've got this very simple equation. Y is a function of x plus some residual. Okay, so if I look at that function or look at that equation, I guess one thing I could do is I could quantify the output variation in a variety of ways. I would prefer to use the standard deviation just because it's on the same scale as the original measurements and it's much easier to interpret. If we think about the standard deviation of y then, and we make some simplifying assumption that there's an independence between the cause x and all other causes, then I could write a mathematical equation for the standard deviation of y given this, what Shannon refers to as the square root sum of squares formula. Okay, so I don't think that's not controversial at all. I try to not have to figure out what the function f of x looks like by just saying, there's some term that corresponds to the standard deviation due to that cause. So that's the first term under the square root sign there. So this is a very simple partitioning of the overall variability kind of formula that's used in a lot of contexts, like the analysis of variance. And so we could look at this formula and try and understand the consequences of variability. How much variability in x, or how much of the variability in y has to be due to x before I can really make substantial progress in reducing the standard deviation of y. So for instance, you could look at this formula and say, suppose I could get rid of the first term underneath the square root sign completely. If I could eliminate all the variability in the output that's due to this cause, whatever x is, then I could eliminate that term in the formula and be left with just the standard deviation due to the rest, due to the r. So that's sort of the idea. And I can quantify that very simply by just making a plot. And so the next slide gives me an example of what this plot would look like. So on the horizontal axis, you can see the ratio of how much of the standard deviation of the overall variability is due to x compared to the overall. And so obviously that goes from 0 to 1. And on the vertical axis, it gives you an idea if I could get rid of, as I mentioned, completely that first term under the square root sign, how much variation could I, what percentage reduction could I get in the standard deviation of the output? And so you can see that plot is a nonlinear curve, right? And that's because of the square root sum of squares formula. But if you look at that graph, I think it becomes very clear that if I'm working on causes that have a fairly small impact, or have a very small impact on the variation in y, say I'm at 0.2 or something, then the overall reduction I could possibly hope for, if I could completely eliminate the effect of that cause, is very small, and I would argue probably not worth the effort. So if we really want to make progress in solving the problem of too much variation in y, we need to be up here. We need to look for causes that are dominant, right? We need to look for causes that have a big impact on the variation in y. And if we don't, we're going to spend a lot of time and effort trying to solve this problem without much impact. So my contention here is that You may not believe the idea that there's a dominant cause, but if you don't have a dominant cause, then trying to solve this problem by addressing non-dominant causes is likely not to be very fruitful. You're not going to end up with much variation reduction. So in a sense, what I'm going to propose is that we're going to assume that there's a dominant cause and hope for the best. Okay, so with that, I hope that I've convinced you. Now I want to move on to the main part of the talk, which is looking at the 7 variation reduction approaches. And maybe just recap, those are the approaches. There's 3 groups there, sort of slightly indented, not indented, but separated. Notice that the first 3 causes, first 3 approaches, which I'm not going to talk about in detail yet, but notice that they're all based on knowledge of the dominant cause. So those are the 3 variation approaches you can use only if you know what the dominant cause is. The next group of 3, feedback control and so on, there are variation reduction approaches that can be used regardless of whether you found the dominant cause or not. So I mentioned that a lot of times people suggest, I want to use the diagnostic journey, look for the cause, then after that I'll look for the solution. Well, it turns out that's not actually necessary. In some situations, I might be able to reduce variation without knowing the dominant cause. I'm going to give you some examples of that. It's harder. You don't have as much process knowledge and so on. And the last variation reduction approach is a slightly different nature. It's what I call changing the process center. So it would be relevant in situations, for instance, like the one I showed with the discrete input dominant cause, where I want to align the output values, the average output values for different levels of the discrete cause. And so there I'm sort of changing the process center for a sub-process, if you will, maybe only ones that are processed by machine number 1 and when there's a whole bunch of machines in parallel or something. Or if you want to change the definition of variation reduction a little bit to variation reduction about some target value, then there also I may want to reduce or just change the process center and have a much better process. So it's slightly different in nature. Anyhow, notice again that this is, I'm looking at the statistical engineering algorithm here. The looking at the variation reduction approaches, the 7 variation reduction approaches happens fairly early in the scheme of things here. In particular, it happens actually before we start this, or the main part of the diagnostic journey, looking for the dominant cause, right? So we're actually considering the variation reduction approaches before I go and look for the dominant cause, partly because of the fact that these 3 on the right-hand side of that big box, they are things I can do without knowing the dominant cause. So I may, in fact, decide to go back into this step and try and understand if I could implement this solution or not. If I don't succeed, I go back and so on. So there's a whole bunch of loops that are trying to be more realistic about how problem solving actually works. But nonetheless, let's go into more detail then on the variation reduction approaches. And what I've got is sort of a concept diagram of how it's going to work. And then I have an example of each of the approaches to give you sort of a bit more concrete idea of how it might work. So the first one is in some sense a catch-all, and probably it seems like what Shannon used to consider, because often in their Shannon system, it seems like once you found the cause, everything you're done, everything's obvious. So this is sort of the idea. Here's the existing process. I found that input that has this large predictive value of the output. This is the dominant cause. What could I do? Well, I could take this input and reduce the variation in that input. It may be the case that I can do that really easily. I may say, tell my supplier, give me better products or whatever. That might not be that easy for them, but it's easy for me, and so on. So there might be things I didn't know that input was important. Now I know it's important. Okay, I'm going to control it better. Other times it might be result in a reformulation of the problem. I originally had a problem, too much variation in the output. Now I'm going to change that problem, reformulate it into too much variation in the input, and go through the whole process again. But the idea is if I could reduce the variation in the input, to say this level, then clearly the variation in the output has been reduced from the original. So it's a pretty easy concept, I think. Let me give you, I have 2 examples here. Maybe I'll skip one in the interest of time, so I'll go to the second one. So here's an example where customers complain about, hubcap damage. Shouldn't happen that your hubcap breaks, with the new car very often. And so the team investigated, found that the dominant cause was sort of an interaction of broken retaining legs on the hubcap and combination of with cold weather and people hitting the curb when they're driving around. So, okay, so now we know the cause. It's this interaction cause. What can we do to solve this problem? It's not quite like the diagram described above, in the sense that it's not a continuous input that I can just reduce variation on. But once the team realized that this was an issue, that the existing material for the hubcap became sort of brittle in cold weather, they decided, oh, okay, well in that case, let's make the hubcaps out of a different material that doesn't become brittle when it's cold weather. So it's sort of, again, obvious solution once I know the cause. Next approach, call this desensitization. So the idea here is, again, we found the input, that's the dominant cause. Here's the same, basically the same plot as I had in the last method, fix the obvious. So again, I could try and solve the problem the same way, but another option is to think about making this, living with the variation in the input. Saying, okay, I know that input is important, but I can't see how I could, in a cost-effective way, reduce the variation in this input easily. So what am I going to do instead? Well, perhaps I could just make the process less sensitive to variation in that input. So this is sort of illustrated by the idea of changing the slope of this relationship to something like this, right? So the idea here is that the variation in the input is the same, but because I've made the process less sensitive to that input variation, the output variation has been reduced correspondingly. So obviously easier said than done. So I need to look for a way of how I could do this. Let me give you an example. So here's an example where the problem was porosity. So little divots, air bubbles, I guess, stuck on the subsurface of the engine block. And through investigation, which is described in more detail in the statistical engineering book, they found that the dominant cause was low pouring temperature, low iron pouring temperature. And so when you had low pouring temperature and when the engine block solidified, it didn't have enough time. It was too cool already. It didn't have enough time for all the air and gases to escape, and so it resulted in its porosity on the surface of the engine block. And these low temperature situations, and maybe obviously we'd like to get rid of those, but they occurred during sort of planned and unplanned stoppages, and it was very difficult to think about a way of eliminating, for instance, those unplanned or planned stoppages, or keeping the iron pouring temperature high during those times without a large capital investment. So instead of doing that, the team decided to think about how could I make this process less sensitive to low pouring temperature. So in other words, I want to have less porosity, even though I'm going to live with this low pouring temperature. So what did? They ran an experiment. They tried a bunch of things. To simplify, I'm looking at only one of the part of the experiment. So they tried changing the core wash to a different brand, basically. And this brand perhaps had allowed the gases in the engine block to escape more readily. And so when the pouring temperature was low, it didn't result in quite as much porosity. It still had an issue, but changing this core wash was the solution that made it, in a sense, made the process less sensitive to pouring temperature variation, or low pouring temperature in this case. So nice example. So moving on, another method where I need to know the dominant cause. Again, similar picture. I've got the input here, the dominant cause of output variation. Now what can I do? Well, rather than either reduce variation in input or change the nature of the relationship with a one-time change, like changing the core wash, what I'm going to do instead is implement a feed-forward controller in this process. So the idea is I have this idea of how the input and output are related, right? I have this plot. So I know that if I'm running the process and I observe a product with an input value down here on the left bottom picture of this plot here, then I know the output likely is also to be small. And so perhaps I can change something in the process to accommodate that in between when I measure the input and when the final output is determined. So I make the prediction, and if the predicted value of the output is not close to the target, say here in the middle, then I would make an adjustment in the way the process runs for that particular product. Now you can imagine this might be really, really expensive, because I'm going to have to do this for a lot of products. Maybe not the ones in the middle here, as you can sort of see by this, but everything else, every time I measure and predict, if the prediction is far away, I'm going to have to change the process in some way. So it's a viable solution. It may be quite expensive, and it involves changing the control plan for my process to include this feedback controller. But here's a picture where obviously it worked. If I can do that successfully, if I can move these parts so that their actual output value ends up close to the target, then I can clearly reduce the variation in the output substantially with this approach. So let me give you an example of how this was implemented in a real world situation. Here I have again simplified the story to make the slide sort of simpler to follow, but this relates to truck pull. So sort of pull on the steering wheel, and there's a sort of ideal value so that the truck will as you're driving along sort of a standard highway will sort of stay straight without you having to do anything to the steering wheel. And so there was too much variation in pull in this particular process. And through investigation, they found that the reason for the pull variation was due to variation in the truck geometry. So like the frame of the car. Before they installed the alignment system, the frames were just off kilter for some trucks. And so as I simplified it here, just showing you how the frame geometry involves a lot of different input characteristics, and they had a complicated formula for taking those geometric features of the frame to try and predict what the pull would be. In this case, I've even simplified the pull to reflect what we call the left caster angle. That's in a sense, in this case, a surrogate for the truck pull. So the picture shows that once I have a prediction from the frame geometry, it's pretty indicative of what the left caster angle will be, and that's going to drive the value of pull for that particular truck. So again, it's more complicated than I'm illustrating here, but I wanted to make a simple plot with only one X and one Y variable. So this is what I came up with. So again, here's the idea. So what could we do with this? Well, again, we could understand this relationship now. We've done a study to understand this relationship. Again, if we then, in the process, we could look at measuring the frame geometry and making the corresponding prediction from the frame geometry with a complicated formula. And then if we got this truck here, we know that their left caster will be quite low relative to what we want. And so we could maybe change the way we install the alignment system, which is sort of exactly what they did. So they use this as a feed-forward controller. So here's what they did. They measured the geometry when they put together the frame. They put a barcode on each frame so that later, when they were installing the alignment system, they could read the barcode. They could use the information from the barcoded information to make a prediction for the left caster angle and the corresponding pull. And if they didn't like what the predicted value was, if the pull was far from what they were hoping for, they would change how they installed the alignment system. And fortunately for them, they knew how to change the pull when they installed the alignment system by just drilling a cam in a slightly different spot when they installed the alignment system. So they had a sophisticated method for figuring out how to make this a corresponding adjustment that would make the predicted pull for that particular truck much closer to the target value. And using this method, despite the fact that it was quite expensive, it resulted in much less pull variation. So a success story. So now moving on to the three different variation reduction approaches that require, or do not require knowledge of the dominant cause, but have other requirements. The first one that I wanted to talk about is feedback control. So the opposite, in a sense. So feed-forward control, you can see was very proactive. It measured the dominant cause, made this prediction, and then made an adjustment if you didn't get close to the target for the output. Feedback control, on the other hand, is reactive. So the idea here is that I'm going to measure the values of the output that I'm seeing now, and if it seems as though the values are sort of away from the target, I will make an adjustment for subsequent parts that I'm going to make, in the hopes that what I'm seeing now in terms of the output is predictive of what's going to happen in the near future. And so here's a kind of process where this kind of a scheme, a feedback controller, might make sense. This is again idealized, but suppose you have a process that drifts upwards with time. Maybe as you're getting a wearing out of some part or cutting tool or something, and so you wanted to figure out when to replace the cutting tool, for instance. So it's drifting up, and this is a fairly predictable pattern. There's some variation, but there's a fairly predictable pattern. So if I measure at this time and I see these values, then I'm pretty sure the next few values will be similar. So as you can notice that if I see values near the bottom here, then the next values are likely to be near the bottom, not close to the target. So I can make an adjustment, after the fact in a sense, too late for the ones I measured, but adjustment for the next parts that I'm producing so that they will end up being closer to the target. So maybe here I would, maybe changing the cutting tool more often as I'm observing this pattern. You might end up with a pattern like this, where it's still drifting upward as time goes by because things are still wearing out, but I'll make this adjustment every once in a while to keep it close to the target. So that's the idea behind feedback control. And the example here is this V6 piston diameter. And you notice that it does have this sort of what I call sort of structural variation in the diameter. Again, this is simplified to looking at only one of the streams and so on, but there's a structural variation. There's a pattern over time in this plot that is exploitable, that allows you to make a prediction over the next little, short-term prediction that'll help you potentially move those values. Say, for instance, I end up here, I measure a first few, and I say, oh, this is far from the target. The next ones, well, before I make those, let's make an adjustment so that they're closer to the target value of around 5 here. So that's sort of the idea. And so they ended up implementing this sort of informal feedback controller. And every 15 minutes they would measure a couple pistons to see where they were at, and if they didn't like what they saw, they would make an adjustment to the way the process ran, so that the next pistons were closer to the target value. So pretty simple idea, but it does require the structural variation in the output. Otherwise, it's not going to work. If you can't make a prediction for the near future, then there's no hope for feedback control. But notice that I didn't need to know why. I don't need to know why. In this case, I was talking about an example with a cutting tool getting worn out, but I don't know why the diameters vary like this. But so long as I know that there is this structural variation, I can make a corresponding prediction for the near future and make it a corresponding adjustment as well, then I can make this process better without even knowing why. Might be nice to know why, but I don't really need to know why. So another approach that's somewhat overlapping with the idea of desensitization, I called it making the process robust. So this is sort of coming from the, I guess, the Taguchi literature. So the idea is basically what I want to do is find a way to reduce variation in this process, make it more robust to variation in the noise, as Taguchi would say. But I don't even know, what the important noise factors are potentially. If I knew the important noise factors, in other words, I knew the dominant cause, then I could use it. I would be better off, I think, using the desensitization approach, where I can build, I didn't go into the details, but where I can build an experiment that exploits the knowledge of the dominant cause to find ways of making the process less sensitive to that variation. It might give me clues about what to change. It helps me understand, make a better plan for the experiment and so on. But as Taguchi has illustrated in some of the work that he's done, and many people follow up studies, there is a way of just using, not knowing what the dominant cause is, but still making the process robust. So basically the idea here, unfortunately, is change the order, I guess, because of the alphabetic order of this. But I got this process to begin with. Here's a box plot of the output, lots of variability. Somehow I'm going to change the process, change one of the, in the Taguchi context, control inputs, so that the process now operates like this instead, less variability. So as I mentioned, there are many examples of this, and I've also been involved in this one here, where we're looking for paint thickness. So paint thickness on the doors was a problem. Turns out the dominant cause, they didn't identify what it was, but they knew that it acted sort of vehicle to vehicle. There was a lot of variation from vehicle to vehicle with this paint thickness. They weren't sure why. They couldn't figure out why. So what they did is they decided, okay, we're just going to try an experiment. We're going to try running the process in a slightly different way. It's hard to understand what to do, so we're going to look at 5 different fixed inputs, run a experiment where each run would have 5 replicates, 5 repeats, sorry, we're painting 5 consecutive car doors. And when we look at the results, rather than look for a way of changing the average value of the thickness, we're going to look for a performance measure that's some measure of variability, and they used the log of the standard deviation of thicknesses over the 5 cars. So again, I could go into a lot more detail on what the experiment looked like and why it would be better, be easier to run the experiment if we knew what the dominant cause was. But here's a success story. They ran this experiment, and they ended up finding that if they changed these settings, these process settings, to the new levels, high, high, low, then by some miracle, the process was better. It didn't have as much door paint thickness variation. So this is not, as I'm sure you've gathered from my discussion here so far, this is not something that an approach that I would really recommend unless we're sort of desperate, but it can work in some circumstances. So the final variation reduction approach is, again, perhaps somewhat controversially, 100% inspection. So how does this work? Oh, sorry, it's not the last one. I guess there's still to move the process center, sorry. But here we're going to try and reduce variation by just eliminating parts that are on the extreme ends of the distribution. And we're going to do that by inspecting parts. We're going to measure the final output value, compare it to some inspection limits that may or may not be equal to the specification limits, and eliminate things that are outside the bounds. Now, clearly, this would only work well if we have a very good measurement system. Otherwise, we're going to be making mistakes. And it really doesn't reduce variation that much unless the inspection limits are quite narrow, in which case we're going to end up with a lot of scrap or rework, so adding to expense. So again, it's not a very desirable approach, but it's used frequently. Here's an example where it was used. So we have these blocked exhaust manifolds. This is a picture that I found off the web, so this is not actually the exhaust manifold we were working on, but sort of gives the idea that these ports, these tubes here, in a very rare circumstance, they could be blocked. There could be something stopping the exhaust or to getting through here, which is very bad for the engine. It doesn't happen very often, fortunately, but it's catastrophic engine failure, so high consequence problem. They spent a lot of time looking for the cause. Very difficult, hard to measure, hard to see what was going on. They were so rare. So they spent about 10 years looking for the cause, just living with this problem. They had somebody dropping marbles through the ports to try and find blocked ports and so on. But in the end, they decided 100% inspection was sort of the only way forward. Sort of an ultrasound system to look through, in a sense, look into those ports to see if they were blocked or not. It was very expensive, but they figured it was worth the effort and the cost. So finally, there's the change of process center approach. So here is illustrated by where we just want to move the histogram over to be closer to the middle of the histogram, is closer to the target. That's one option. Another option, as I mentioned, is I want to align sub-processes so that I have a discrete cause. I can make the overall process output variation less. So here's an example where we had leaky batteries, customer complaints. Turns out they found that the cause of leaks was sort of low tensile strength. So they reformulated this problem to move the center. They wanted to make these seals stronger. So their goal in this case was to find a way of making the seal stronger. This is a classic example of an experiment that I might want to do. I want to move the average seal strength. I could try changing the way I'm putting these battery seals together. Again, skipping the details of the study that they did, but they tried 3 different changes to the process, and they found that low melt temperature resulted in increased seal strength. And so this was their solution. So we're kind of running out of time, but here I am at the wrap up. So hopefully we can move to questions soon. So here's what I sort of talked about. I talked about some systematic problem solving systems, algorithms. All of the ones that we talked about today are not really just a collection of tools, but trying to help people understand sort of what steps to go through in solving problems. I argued that the more focused it is, the more prescriptive we can be, and that has certain advantages. Of course, also disadvantages, because it means, of course, it's less applicable. It's not as widely usable, but there are some advantages. I discussed this idea of separating the search for the cause from the search for the solution, and how that relates to these ideas of the fixed and varying inputs. And I also suggested that in most processes there is a dominant cause, which you may or may not believe. And then I talked in more detail about the various what I claim are the 7 variation reduction approaches. And here is sort of a schematic to try and, I don't know how good they are, to try and give you an idea of remind you, I guess, of what how they work. There are obviously some overlaps between these areas, these different approaches and different problems, but I'm happy to take questions now. And thank you.
All right. Well, thank you, Stefan. That was an excellent talk. We do have a number of questions here, so I think I'm going to go through them chronologically. The first one was back when you were talking about just the different frameworks for problem solving, and then in yours in particular, someone asks, where do you think the idea of Poka-yoke fits in? And this was a term I wasn't familiar with, and in case anyone else in the audience is not, I Googled it, and so it's this idea and term that seems to have been popularized at Toyota, which is sort of to enable error handling and sort of preventative measures from human error actually occurring. So where do you think that fits in?
Yeah, I guess, well, certainly that's maybe perhaps that falls into the category of the fix the obvious. You try and make sure that the mistakes don't happen in the first place. So if you know what kind of mistakes are frequently occurring, then you could try and set up a system where they don't occur anymore. I guess in my context, that would fit into the sort of fix the obvious.
Okay. So the next question was about the measurement system. You show that as sort of the second step in your schematic of the algorithm. So the question was, can that actually be a cause of variation itself? So maybe you can talk a little bit about the importance of the measurement system to your algorithm and finding the dominant cause.
Yeah, so clearly the assessing the measurement systems are clearly very important as a separate step just for that. And certainly the variation in the output that I was showing on all these various plots so far could have been due to just variation in measurement systems. So that's one reason why early on in the process, I suggest we check the measurement system and do some kind of classic measurement system assessment to see how much variation is being introduced by the measurement system. And it's critically important because, of course, that's our view on the process, right? If we can't measure things precisely, then it's really hard to understand what else might be causing variability. So we want to have a good measurement system, and we want to check that early on to make sure that it's good. And if it's not good, then we could actually potentially solve the problem by improving the measurement system, or at least we want to spend some time and effort making our measurement system better before we proceed to trying to find the other important causes in the process. But measurement systems are critical.
Okay, the next one is more a comment, I think, than a question. When you're talking about sort of justifying the existence of a dominant cause, you use the idea of the trivial many versus the vital few. There's a suggestion here that maybe the dominant cause can also be justified through the lens of Occam's razor. I wonder if that's something you've thought about.
Well, yeah, so Occam's razor, as I understand it, basically sort of the simplest answer is often the right one. So yeah, potentially. I mean, I'm not sure. I haven't really given that much thought. Having a single dominant cause is sort of the ideal situation in a sense that then it focuses your effort on how to make the process better. Whether that's necessarily realistic, that there should be a simple solution or a simple answer to what the cause of variation is maybe a more philosophical question that I don't really have an answer to, but it's potentially that's another way of justifying, or at least explaining why dominant cause might make sense. I think maybe in my view, the most compelling argument is that the square root sum of squares plot that I showed, that if you don't have the dominant cause, well, it's really difficult to make progress. So we're in a very unfortunate situation if it's not the case.
Mm-hmm. Okay, and then speaking of solutions, you've talked through several different approaches. Do you have experience or guidance on maybe combining more than one of those strategies together? Like, I could imagine changing the variability on that dominant cause and then also desensitizing the process. If you could do that simultaneously, you might have a better solution than if you did either of these things on their own.
Yeah, so absolutely. So you definitely can combine these various solution approaches together. Some combinations are, of course, harder to implement together, like feed forward control and feedback control at the same time seems perhaps difficult. But many of the other approaches, yes, you could reduce variation. You could reduce variation in the cause that you found, but maybe it's not possible to do or really expensive to reduce variation a lot. So then maybe you could add another one of the approaches to get rid of some more variability and so on. So definitely looking at combinations is feasible and potentially desirable. You do have to be careful though that, there's every time you make changes to the process, I've sort of focused on looking at sort of one process output at a time. You do have to worry about what I like to refer to as sort of side effects. I might change something in the process to make it better for the piston diameter, but then maybe the hardness of the pistons is impacted in a negative way. And so I have to be careful about making a lot of process changes, especially all at once, without having sort of proved out that this solution is not just helping me for the one particular output I'm looking at now, but for broad across the gamut of all the important output characteristics of interest.
Okay, we're almost out of time, but there is one more question, so I do want to ask it. Someone asked if you're doing variation reduction, and in particular, after having done something like an application of your algorithm, you found a solution, you've reduced variation, where do you see control charting and process monitoring fitting into that? Is that something that should be done in an ongoing way during or after a variation reduction endeavor?
Okay, that's a really good question. I don't give much emphasis to control charts in the algorithm, in the sense that I don't think it's a very strong method of finding the causes and finding solutions, but it has a role potentially in sort of holding what I call holding the gains. So once I've made changes in the process, especially if it's things like, oh, I found that the process drifted out of control or drifted away because of I didn't pay attention to the fact that this thing got loose or something. Then if I want to avoid that problem in the future, one simple sort of I could fix it now, realizing that maybe this problem is going to reoccur because I haven't permanently got rid of the possibility. So I might monitor the process with a control chart to give me a quick heads up that something might be going wrong, and then I better check whether this thing has gotten loose again or something like that. So I think it has a role to play in keeping the gains that you've made from your process improvement projects, but it's not a really strong method. It's too passive in my view to actually, if you task by your manager, I got too much variation in this process, figure out why it's got so much variability and solve the problem. It's too passive approach. I think you need a more active approach when you're trying to solve process improvement problems.
Yeah. All right, well, there are a couple other questions, but I think we've run out of time. So I think I'll invite those people who still have questions. I'm sure Stefan will be happy to answer them by email if you contact him directly. I'm going to use that as a plug to encourage you to go to the ISEA webpage. You can find it at ISEA-Change.org. You can go there, you can learn a lot about what ISEA and statistical engineering is. You can register to become a member of the association if you haven't already. It's free to do so, so I encourage you to do that. Stefan already promoted one of the nice features of being a member. There is a member-only section where you have access to a lot of exclusive content, like the PDF of his book. So I encourage you to go to that website for more information and to learn about the upcoming events. And there is contact information for the organization's board. Stefan, as I said at the beginning, is the chair of the association. So if you want to contact him directly, please visit the website and you can see his contact information there. And so with that, I'd like to thank all of you for attending, for your attention, for your questions, and then also to Stefan for a really wonderful talk. So thanks, everybody.
Yeah, thank you.